We're continuing our morning session, and the second talk will be given by Yves André, who is also from CNRS, Director of the Research from Paris-Sorbonne. And André also has a number of prizes. In 2011, he got a prize of Academy of Sciences, the Français, the Sto Bleutet Prize, and in 2018, he was invited speaker at ICM in Rio de Janeiro. And today he will speak on Non-abelian Rees construction and motives. And according to our ancient Chinese tradition, let's give a warm welcome to Yves now. I'm sorry, I forgot to do it for the first speaker, so I'm sorry about that. But...
Thank you very much for the introduction. So, before speaking about the non-abelian Rees construction, let me recall the standard classical Rees construction. Well, it worked. It worked 1 minute ago.
You put this one.
No, this one.
No, you want to move it?
Yeah, yes. Okay. Okay, that's okay. Thank you. Okay, in this talk, for the whole talk, K will be an algebraically closed field of characteristic 0. And the classical Rees construction deals with the category of filtered vector space over K, where the objects are K vector spaces with decreasing sequence of subspaces, which is separated and exhaustive. And the morphisms are just K linear maps which preserve the filtration. So this is a rigid monoidal category, which is non-abelian. But if one passes to the graded underlying space, we get a monoidal functor, which I'll denote by GR, between this category of filter vector space and the category of graded vector space, which is abelian. And the Rees construction, which appears already in a paper by Rees and Northcott from 1954, in the special case of IDIC filtration in commutative algebra, is the following. We start from a filtered vector space, and we construct a certain Kx submodule of this module, V tensor the Laurent polynomial, which is defined in the following way: x to the minus I k of x, tensor Fi V. And this submodule, in fact, can be interpreted as a GM equivariant vector bundle on the affine line viewed as the spectrum of k of x. So this construction starts from a filtered vector space and gives rise to GM equivariant vector bundle on the affine line, where the affine line is given the standard action of GM. So, and this gives rise to a commutative diagram of tensor functors, which is like this. So here we have the vertical functor is our passing to the grading. Here we have a GM equivariant vector bundle on the affine line. One may take the fiber at the point 0 of the affine line. This gives rise to graded vector space, which are essentially the same as representation of GM. And this diagram commutes, and the horizontal functors are equivalent. If instead of taking the fiber at 0, one takes the fiber at 1, in fact, one gets a new functor, which is an embedding, a non-full embedding of this category of filter vector space into the abelian category of vector space over K. So that's the categorical meaning of the classical Rees construction. Here, the affine line appears as a deformation space between our two categories, the category of filter vector space and the category of graded vector space, the latter being exactly the quotient of this tensor category of filter vector space by its maximal tensor ideal. Now, the non-abelian analogues of this classical Rees construction, which I'm about to speak about, look for similar features, but with group GM replaced by an arbitrary reductive group G. So there are two basic questions. The first one is what will, in this situation, replace the affine line as a deformation space, in fact, between a certain category and monoidal category and its quotient by the maximal tensor ideal. That's the first question. And the second question is how to describe concretely tensor categories of equivariant vector bundles, which I denote by vec Gx, on more general space X with an action of G. In the Rees case, if G is GM, X is affine line, the concrete description is just the description as a category of filter vector space. I will start by question 2. Which was given a broad answer, first by Kliashko, in the special case where X is a toric variety, and then by Ashok, more recently, in the more general case of spherical varieties. I will recall what is a spherical variety. But first, let me give some definition. So now G is a reductive group of our algebraically closed field K of characteristic 0. And the fundamental concept in this talk is the concept of pre-homogeneous G variety. Pre-homogeneous G variety is the G variety X, which has a dense orbit X naught, which and this X naught is a homogeneous G variety, of course. So this is a kind of partial compactification of homogeneous space. Now, spherical G variety is a special kind of pre-homogeneous G variety, which remains pre-homogeneous if one restricts the action of G to some Borel subgroup, B of G. So this is a geometrical definition of spherical variety, but there is an equivalent condition, which is a more representation theoretic flavor, is the following one. For any representation of G, W, the H invariant in W form a space of dimension less or equal to 1.
This is a condition for it to be spherical.
Spherical, yes. And as you see, this depends only on X naught, in fact, on G and H. And a very important definition for the sequel is the definition of fixed pointed G variety is a G variety which admits a unique G fixed point. So there is an extended theory of very well developed theory of spherical varieties by Brion, Luna, Wust, and other people. And this theory gives a combinatorial description of spherical G varieties in terms of certain one-parameter subgroups of G and some other data, which are called colors in the theories. Now the theorem of Ashok, which answers my question 2 in the spherical case, is that for any fixed-pointed affine spherical G variety, the tensor category of equivariant vector bundle on X is equivalent to a category whose objects are representation of G, but whose morphism are only H linear maps, which preserve certain filtration canonically attached to the one-parameter subgroups. So this is very close to the original Rees construction, but here you have several filtrations instead of just one. Well, of course, in the classical Rees construction, G was Gm and H was just a trivial group. So some comments about the definitions. So first of all, if one starts with a homogeneous G variety, X naught, so G ordered out by H, the question of the existence of an affine pre-homogeneous G variety with open orbit X naught is the existence is equivalent to the fact that X naught is quasi-affine. So it embeds in some affine variety. Of course, this is a necessary condition, but it's not so trivial to see that it is sufficient. Well, and moreover, this condition that X naught is quasi-affine can be read on the subgroup H of G. This is exactly equivalent to the fact that H is an observable subgroup of G, which means that any representation of H can be embedded in a representation of the bigger group G. So now sometimes X naught itself can be affine, so and this is equivalent to the fact that H is reductive by the celebrated Matsushima theorem. But there is a criterion for the existence of some affine pre-homogeneous space, which is different from X. So now X is X naught. I'm sorry, X naught. So X naught is given. It's supposed to be quasi-affine. Then there exists an affine pre-homogeneous X, which is different from X0, if and only if for every reductive subgroup H. I'm sorry, there is a mistake. H dash of X H. So the centralizer of S dash in G, mod out by the intersection of H dash with this centralization, is an infinite loop. This is a deep criterion due to Luna, which will re-enter the picture at the end of the talk. This is a bit technical, but well, it's important to see that if you can read this criterion and, so in the positive sense, that if there exists some reductive subgroup H dash of H, so that this quotient is finite, then X should be X0. So there is no other affine embedding. But there is a complement by Arsensev that in that case, if there exists an X0, which is an X which is different from a X0 and which is affine and pre-homogeneous, then one may assume, in addition, that such an X exists which is fixed pointed. So let us now deal with the first question, which was the question of what is the deformation space in the case of a non-abelian Rees construction, that is, when you replace GM by an arbitrary reductive group. And a quite general answer was given by Peter O'Sullivan. So now one starts with a rigid K-linear monoidal category, which is even in the sense that any object is killed by some exterior power. One can prove that such a monoidal category has a maximal tensor ideal, such that the quotient by this ideal, which is a category which has exactly the same object, but the space of morphism is just a quotient, is then a semi-simple Tanakian category. Well, I should have said here that C is supposed to be pseudo-abelian, so that so idempotents have an image. Okay, and one can moreover prove that there exists an essentially unique monoidal section, sigma of the projection from C to C bar, which is the identity on objects. Then such a section of the projection admits a right ind inverse, which I denote by theta. And if one denotes by O of x the image by theta of the unit object of the category C bar, C, or NC, then this is an algebra in ind bar C. So that one can consider the space X, which is spec of theta of 1, and this is a fixed pointed affine G variety, and C is equivalent, so this is a result by O'Sullivan, is equivalent to the category of so G equivariant vector bundles on X. So an example, very simple example, the category C of vector bundles over the projective line. So by a famous theorem of Grothendieck, the objects are just the sums of the O of n's, line bundles. In this case, the group G is GM. The deformation space between C and C bar is equivalent to the category of graded space, is the affine plane X, where GM acts on so by homothesis on both coordinates, and C is equivalent to the category. So C, the category of vector bundle over P1, is equivalent to the category of GM equivariant vector bundle on the affine space. So that's. And now taking the fiber at the generic point of P1, embed C into the vector bundle over K of X. Whereas if you take the fiber at the point 0, the origin of the affine plane, you get the projection from C to bar C. There is a difference here between this situation and the original construction, is that the deformation space is no longer a pre-homogeneous G variety. The affine plane is not pre-homogeneous under GM. And moreover, the category C, the vector bundle over the projective line, does not embed into the category of vector bundle over K. Only to the category vector bundle over K of X. When I say embed, I mean not necessarily fully. So in the sequel, I will state some condition on C, which brings the situation more closer to the original Rees construction, so that C is equivalent to the certain category of G equivariant vector bundle over a fixed pointed affine pre-homogeneous variety X, and which makes things amenable to computation, as we will see.
Sorry, what's a factor from C to C bar in the sequence?
Alors, C bar is the quotient of C by the maximal tensor ideal. The tensor ideal is a set of morphism which is stable by composition and by tensor product. But the C and the C bar have exactly the same object. So you just quotient the space of morphism by a certain ideal.
Okay. The C bar is the module over DM.
Yes, so this is the graded vector space, just as in the case of
So in this
Rees
example,
concept.
geometrically, can you give a geometric interpretation for this function from C to C?
Yes, O of n correspond to the line with the grading n. So just any vector bundle is a sum of O of n's, and you just replace this by the graded vector space with the corresponding grading. So now here is the set of conditions. So we start with a reductive group over K. We fix, we give ourselves a fixed pointed affine pre-homogeneous G variety X with open orbit X naught, which is naturally a homogeneous G. Then the category C, which in this slide denotes the category of G equivariant vector bundle on X, has the following properties. So this is a pseudo-abelian rigid tensor category with properties P1, P2, and P3. P1 says that C tensor embeds into the category of vector space over K just by taking the fiber at any point in X naught, give you a faithful factor. P2 is that there exists a certain object in C such that any other object is a direct summand in some tensor construction on this object V. So this is some kind of, well, finiteness statement. And the third condition, P3, is also a finiteness condition. There exists an integer L such that for any pair of integers M and L, the morphism in C between the unit object and the space of tensor Tmn, the mixed tensor on V, is tensor generated by similar morphism, but with a mixed tensor of by degree limited by L. So we have three properties, and the theorem is that for any such pseudo-abelian rigid tensor category C, which satisfies these three properties, the O'Sullivan construction provides now a fixed pointed affine pre-homogeneous variety, Gx, not as in the case of vector bundles of P1, which is a counterexample. And here it gives, moreover, rise to a commutative diagram of tensor functor, the horizontal one being equivalence, exactly as in the context of the classical Rees construction. Here you have C, it's quotient by the maximal tensor ideal. In the Rees case, C was just a filter vector space, bar C the graded vector space. And on the right, you have the G equivariant vector bundle on X. And here you take the vertical row is taking the fiber at the point, let's say 0, which is the unique fixed point in X under G. And the quotient is equivalent to the category representation of G. And this provides two anti-equivalents, the kind of Galois correspondence between such tensor categories, those which satisfy the three conditions, and fixed-pointed affine pre-homogeneous varieties.
What property fails for the vector bundles on T1?
Yes, exactly.
Which one fails?
The first one, which says that there is a faithful functor to vec k. There is a faithful functor to vec k of x in the case of vector field. See, only this fails. Pseudo-abelian means that it's idempotent complete. So if you have a projector, you have the image and the kernel. So this looks very abstract, but in fact there is a very concrete formula for this x, or rather for this for the ring of function on x, which is this formula. This is the direct sum, at least. So this is an object in the bar C, which is in representation of G. So the representation of G may be not finite dimensional. And here the V runs over all isomorphic class of indecomposable objects in C. V bar denotes the corresponding irreducible G representation. So this is an explicit formula for this module, but there is also more involved, but as explicit formula for the product, which gives the structure of algebra. So let me give an example, very simple example. C is the category, the Tannian category of representation of the group GA, the additive group. Here, the G is a group SL2. This is a version of the famous Jacobson-Morozov theorem. And the deformation between space between C and C bar, so C is representation of GA, C bar is representation of SL2, is the once again the affine plane X, but with action of SL2 now, not of GM. So this is a pre-homogeneous affine variety, fixed pointed by 0. The X naught is affine space minus 0. This is G over H, where H is equivalent to, is isomorphic to the upper triangular matrix group GA, and C is equivalent to the category of SL2 equivariant vector bundles over the affine plane. So this is maybe one of the simplest non-trivial examples. So now some properties of this Galois correspondence. One can read the properties of the functor on the side of the category, on the properties of the G pre-homogeneous space. So for instance, the functor, tensor functor C to C dash is faithful if and only if the image of the corresponding map, which goes in the opposite direction between pre-homogeneous space, meets open orbit. It is fully faithful if and only if the corresponding map between the group in the opposite direction is surjective, and X is a quotient in the sense of the space of a closed orbit for the kernel of F. One can also read when this functor is full and essentially surjective, this arises if and only if, in fact, the two groups are isomorphic, and the map between X dash to X is a closed immersion of the G subvariety. And finally, I turn back to my spherical varieties. X is spherical if and only if for every indecomposable object V in the category C, the dimension over K of the space of morphism between the unit object and V is less or equal to 1. If this category, this finite category, finiteness condition, P3 is a bit annoying, a bit difficult to check. So if one drops this condition, the situation is almost the same. Just instead of X being really a pre-homogeneous space, you get a countable limit of a tower of fixed-pointed pre-homogeneous variety Xn, which have all the same group G and the same orbit X naught, same open orbit. So the situation, so the condition P3 is not so important. So let me turn to motive and apply all this discussion to motives, pure motives. So Grothendieck motives for homological equivalence in this talk form a pseudo-abelian rigid tensor category, which is built from projective varieties over a field small k. The morphism being constructed by algebraic correspondence modulo homological equivalence, and I take them with coefficient in our field K. So the field of coefficient of a cohomology theory, which I will assume here to be algebraically closed, characteristic 0. So any tensor subcategory C of a motive which is cut on products of finitely many varieties, let's say Ym, satisfies the condition P2. But in order to have the condition P1, which means an embedding, so a faithful functor to the category of vector space over K, this is this famous problem that you get normally a functor to the category of super vector space. And so you have to twist the commutativity constraint, assuming that the QNet projector of the even part of the cohomology are algebraic. Assume this for the moment, and let's try to apply the non-abelian Rees construction so that we get Gx such that the category of motive is equivalent to a category of G equivariant vector bundle on X. So G is what can be called the numerical motivic Galois group. This is the Tanakian group of the category C bar of motives for numerical equivalence cut on products of this variety Yn. And what is X? This mysterious X, which is provided by the O'Sullivan construction. This is a limit because we don't have maybe condition P3, a limit of Xn, limit of tower of fixed-pointed affine pre-homogeneous varieties with the same G and the same open orbit G over H. So now, what is H? If the QNet projector are algebraic, and the characteristic of the base field K is 0, then H is just what I call the motivated Galois groups. This is the Tanakian group of the category obtained from C, from the category of Grothendieck motifs, by adding formally the inverse of the Lefschetz operators. And doing this in characteristic 0, one gets a Tanakian semi-simple category. So G is a numerical motivic Galois group, H is a motivated Galois group. So now there is this famous Grothendieck standard conjecture J, which says that it predicts that the homological equivalence is the same as numerical equivalence for, let's say, our category of motif C. This is equivalent to the fact that this X, this pre-homogeneous is just a point. But as everybody knows, no progress has been made on this conjecture except in a very few special cases. And moreover, no evidence, no general evidence has been provided for this conjecture, in fact. So it seems interesting, I think, to look at the picture which can emerge if the geometry of this pre-homogeneous variety xn, if they are not reduced to a point. So if this standard conjecture does not hold. Then, in any case, the G orbits in X correspond to adequate equivalence relation, which are intermediate, correspond exactly, so there is a big bijection, with equivalence relation intermediate between homological equivalence and numerical equivalence. And one knows that there are finitely many if X is spherical. Yes, this is not clear. Yes, you are right. When I say X spherical, I suppose that the tower is finite. Otherwise, one has to yes. So an example. It's well known that there is a close connection between the Hodge conjecture for complex abelian varieties and the standard conjecture D for the total space, which I denote by F y to S, of a compact pencil of abelian varieties of the same type as A. And this leads to theorems that Hodge cycles on complex abelian varieties are motivated. If we try to apply the non-abelian Rees construction to this question, one is faced with a problem. So how to show, first of all, that the even QNet projector is algebraic. So here there is a trick, a very simple trick. You may replace the base curve by a two covering. So in concrete example, this the motif the family of motifs which you cut has a trivial monodromy, and you see immediately that the involution now acts of this two covering acts trivially on the even part, but not on the even, because this is like this one is like S0 or 2 of S, and this one H1 of S. So in any case, one can play with this and look at which kind of X one can get. And in fact, one can compute explicitly many cases. For instance, when we look at families of abelian pencils of Veil type, which are attached to a CM field F, they were introduced in the case F is the quadratic imaginary field by Veil, in order to give a potential counterexample to the Hodge conjecture. Then the generalized Rees construction provides an X, which is either a point if the Veil cycle, those potential counterexamples are indeed algebraic. And this is the case, in fact, if F is quadratic by a quite recent theorem of Markman, but it's still open for a bigger CM field. Or the alternative, if the Hodge conjecture is not true, you get that these varieties Xn are three-dimensional affine toric varieties whose defining cones can be explicited. So now to finish, I will give an application of this theory, of this non-abelian Rees construction. In the other direction, to prove the conjecture, the standard conjecture D in a special case, by applying the theory of affine fixed-pointed pre-homogeneous varieties. So the theorem is the following one. you take an abelian variety over a field K, whose endomorphism ring is just Z. In fact, one may assume more generally that the center of the endomorphism ring is just Z. Then numerical equivalence is the same as homological equivalence for algebraic correspondence on powers of A. Of course, this is well known in characteristic 0 by Lieberman. No assumption on the but it's new in characteristic P. So the sketch is, of proof is the following one. One may assume that K is finitely generated. One can take K for capital K, the field of QL bar. Now, H, our group H, contains the Zariski closure of, which I denote by H dash of the image of Galois. And this group H dash is reductive, and it has the same endomorphism H1 as G by the theorem of Tate and Sarin. Since the endomorphism of A reduced to Z, one can show easily that this implies that the centralizer in G of H dash is the center of H dash. And one may apply Luna's criterion on affine embeddings of homogeneous space, which proves that X is X naught. But since it is fixed pointed, this cannot be the case, so it's unless it's reduced to a point. So the main argument here is Luna's criterion. So I think I will stop here. So thank you.
We have a lot of time for questions.
In these considerations, is it important the exact structure and the category of vector bundles, covariant vector bundles? I mean, short exact sequences of vector bundles. Are they?
In fact, yes, it often happens that that these categories are quasi-abelian or quasi-Tanakian, but it plays no role in this theory, in fact. No, I don't use it. No.
Somebody else?
If you remain agnostic about homological equivalence being numerical equivalence, this construction seems to give some kind of partial order by specialization on all the intermediate relations.
Yes, you can describe this intermediate relation in geometric terms because in many cases, I gave an example, but you can consider the Kugasateki construction, many cases where you want to prove that these cycles are algebraic. You can, in all concrete cases, you can compute explicitly the X, which is always either a point or something that you can compute explicitly. There is always this alternative. You wish X would be a point, this would be conjecture D, but otherwise you have a very nice landscape.
I see. You mean for certain subcategories cut out by finitely many objects, it might not be, there are examples where it's not a point. Is that what you're saying? Or?
What I say is that in concrete computation, you at the end you always find, if everything goes well, an alternative. It is either a point or something higher dimension, but which you can compute explicitly. Only in very special case, like in this theorem, you find that there is only a possibility for a point. But in general, you have an alternative. And in the second part of the, if this is not a point, you can describe this X, which is the limit of Xn, and you can describe the Xn very precisely. You can, in many cases, this is a spherical variety. You can describe it by combinatorial data, know all orbits which correspond to intermediate.
Thank you.
Any other questions? If not, let's thank our speaker again. And the last talk of the morning session will start 10